Okay, good afternoon. Any questions, firstly, on the design homework which is circulating around? Okay. Another, I've changed the slides of this particular module, which we had started last time around on Wednesday. So they are at the same URL. There are just some additional slides, so you might want to print them out. So the plan for today is I'm going to reiterate some of the material I had started on. So because I think this concept of state and sequential circuits and finite state machines is a little bit tricky. So hopefully second time around, better chances of me conveying the message. And I'll also talk about some of the newer tools that help design these circuits. So that also brings me to another email announcement or Piazza announcement I sent out, which is there is a tool called FIZZIM, F-I-Z-Z-I-M, which we would like you to install. It's again just a straightforward download. Play with it if you can, but bring your laptop to the Friday's discussion section because Paul and Salma are going to sort of walk through that and kind of use that for this portion of the course. Okay, so last time around, what we had sort of started looking into was these sequential circuits, and the idea being that these are circuits that remember state, remember history. And so we had introduced this concept that at any given point in time, my system can remember some bits about the past. It cannot remember everything about the past because that would require infinite amount of storage, but some relevant portion. And we had talked about some examples, and we'll go some more today where the relevant portion of the past that matters for a particular application can be reduced to a small number of bits, and then we act upon those. And the idea then is that our system ends up looking like there is this element which is capable of storing information, and the way it works is every time the clock ticks, it looks at its input, and whatever is on the input, it stores in it. At all other times, what's doing is that whatever is in storage, it's putting it out on the output. So the output of this module is what we think of as the current state. This is what the current status of the system is. And then we use some combinational logic to do two things. Number one, we generate what the next state is. So the idea is that we are observing the input. So based upon the input and the current state, we decide what the next state is going to be, which is out here on the right hand side. And the other thing is we also use this combinational circuit to also generate a new output, which is what we send to the external world. So its sequential circuit really is then combinational logic and then this memory element which is sitting in a feedback loop. So we had talked about that, and one other thing I had mentioned was that one of the very common ways of implementing this memory element is something called D flip-flop. So D flip-flop is a very is made using our good old gates and all, but ultimately in its most simplified form, what it is it is a device which has two inputs and an output. It has a data input. It has a data output, which is called Q commonly, and then there is a clock. Clock is typically shown by this kind of a triangle out here. And the idea is that inside it is some storage. Every time the clock ticks, and by that what I mean is that we designate one of the edges to be the tick. So we say when the clock goes from 0 to 1, or maybe the other way around, 1 to 0. If it is 1 to 0, you will see a bubble out here. It's inverted. But normally, so this thing indicates that every time there's a positive edge on the clock, 0 to 1, then whatever is on the data line gets stored out here in this flip-flop. And at all times, the Q is whatever reflects whatever is in the storage. Okay, so at all times, it's basically outputting whatever is in the storage, but the storage is updated only when there is a tick out here. And then there are modified embellished versions of these D flip-flops. So there might be extra pins which can say, do not look at the clock, so you can disable the flip-flop. Sometimes they have pins for set and reset, so that whenever they are high, the storage is set to 0 or set to 1, irrespective of whatever is on the input. And then another very common feature is that not only is the output given, but also the complementary version of the output. So if you go to Logisim and if you put up the D flip-flop, that's what you would see. In fact, so the other thing is, maybe this is a slide which I did not have last time, but hopefully this helps understand things a little bit better. So I have a flip-flop here where there is a clock, data Q, QB stands for Q bar, so it's the complement, and then I have a reset signal also. So when we start out, reset is high, so the flip-flop, if you see the output value of the flip-flop Q is 0, and Q bar is high. Okay, so that's what's happening in this portion, and D does not matter. D may be some either 0 or 1, we don't care. At some point in time, which is denoted out here, reset goes to 0. At that point, the reset is no longer active, and then and at that time, we also have to make sure that D has some proper value. So the idea is, in the startup phase of the system, soon after you are powered up, you will keep the reset high while your Q is getting ready. And once Q is ready, you bring down the reset to below. So at this stage, D is 1, but see how Q stays at 0 because a clock tick hasn't come yet. This is a positive clock thing. So first clock edge comes out here at this point. So you see clock is going from 0 to 1. And at that point in time, what happens is that the flip-flop looks at its input, D, which is 1. It stores that value D inside the flip-flop, and Q reflects whatever is inside the flip-flop. So as you see out here, Q rises. So Q goes from 0 to 1. And at the same time, Q bar goes from 1 to 0. So what's happening is the clock tick causes storage to happen, and once the storage is updated, Q goes high, Q bar goes low. Reset being 0 has no effect at this stage. So now, even though this timing diagram is showing everything happening kind of instantaneously, there's a causal sequence which is happening. Clock tick happens, that causes the storage to be updated, which in turn causes the outputs to be updated. Okay, so there's a sequence of events which is happening. So if you were to zoom down into picosecond scale things, you would see that the clock edge comes first, and then Q and Q bar come a little bit later. Then things proceed. Clock goes down, but since this is a positive edge D flip-flop, nothing really happens. Next clock edge comes. Well, we are already 1, so it will have no effect because D has not changed. Somewhere in the middle of the next clock, D goes to 0. So D went to 0 out here. But the effect of this will not be felt until the flip-flop next looks at the input, which is going to be the next time there is a rising clock edge. And that's what we see indeed. The next time there's a rising clock edge, at that point in time, Q and Q bar change. And the same process, I don't think I have anything else in this short little example. So very important point that I can change the D input arbitrarily, but its effect, the only time it is looked at is when the clock edge comes. And at that instant, it kind of looks at the clock edge, at the clock edge, the flip-flop looks at the input and updates its storage, its memory, as well as its output. Outside that clock edge, you can arbitrarily change D. And in real flip-flops, what happen is they usually have they'll have some sort of a requirement which says you cannot change D in a little window around the clock edge, otherwise bad things happen. And we'll talk about that later in the course. So there's a narrow window in which you have to kind of keep it stable.
Is this only for the rising clock edge?
This is for the rising. So see, in this case, nothing is happening at the falling clock edge. Okay, there can be flip-flops which are sensitive to downgoing edge. Okay, the only difference you would see is in the symbol. It's not just a triangle. There's going to be a bubble also out there, which indicates inverted. Okay, so in a negative edge sensitive flip-flop, it looks at the input at the falling edge of the clock. Okay, you could also imagine flip-flops which are sensitive to both edges, rising edge and falling edge. They are usually not used unless there is some pretty weird design. In fact, designing them is kind of a little bit tricky. So in any case, I mean, that's more of a gotcha type designs, but otherwise normally designs would say it's either rising edge or falling edge type. Yeah.
Is that so? The caret is standard to mean rising edge on the.
Caret stands for rising. Caret means A is a clock and B is a rising edge. Okay. So I'm skipping over material which I had covered last time to kind of focus on the important points, which kind of summarize the main thing. So, okay. The other thing was we had talked. I talked about this example of a sequential circuit, which is a specific instance of what we had seen before. So in this case, I have my state memory, which is the state, which is n bits, and I have an adder. And what I do is every time the next state is current state. So see how the adder, one of the inputs of the adder is the output of the state register, and the other input is 1. So what's happening is in the next state is always the current state incremented by 1 modulo 2 to the power n, because we are doing an n-bit addition only. So at every clock tick, we would expect the new state value to be the old state value plus 1. And indeed, that's going to happen. We start out with some value arbitrarily, 0, 1, 0, let's say. Every time the clock ticks, see how 0, 1, 0 goes to 0, 1, 1, then to 1, 0, 0, and so on and so forth. Ultimately, it hits 1, 1, 1, at which point adding 1 will bring it back to 0, 0, 0, and the whole process will keep going. This is essential. This is an incrementer. Every clock tick, it's incrementing. So its functionality could be said as, you could describe it as number of clock ticks which have come since the system started. Okay, that's what this thing is doing. Modulo 2 to the power n, because we are dealing with a finite number of bits here. Okay, now what I want to drive towards is that this is a sequential circuit point of view, and we are dealing with flip-flops and gates and stuff like that. But one thing which we saw in the early part of the course is that when you start thinking of a combinational system, you don't immediately think of gates and all. You think of a problem description. We kind of tell you designs, whatever, some tasks, some higher level stuff. I want to design, like in the homework, design assignment, a Morse code encoder, decoder. That's the level at which we like to think of systems, and then we gradually kind of refine, take that description and decide what's the algorithm, and then we go further, and then we decide how to implement it in gates and all, and bring to bear Carnot maps or logisims analysis and whatnot. What we want to develop now is what is a similar strategy for sequential circuits. Clearly, if every problem we were to think in terms of just flip-flops and this combinational logic, that's too low level. So one very common formalism for this is something called, thinking of it as something called a state machine. And that's what I had introduced last time, but we're going to spend more time with some additional slides this time around. So to motivate that, kind of the idea is, again, we are looking at the very same circuit. Sorry, not the very same circuit. I have a circuit out here. Hang on a second. Have I messed things up out here? Yeah. So I have a circuit out here which has 1 bit of input in and 2 bits of state. So 0, 0, 0, 1, 1, 0, 1, 1, and I have a 1 bit of output. And what I've done is I have given you the behavior of this combinational logic, what this combinational logic does. You can think of it as the truth table for this combinational logic. How we came to it, for now don't worry, but let's say this is what it is, okay? That I have a sequential circuit whose combinational logic behaves like this, and it has 1 bit of input, 1 bit of output. So in particular, if you look at this combinational logic, it has 3 bits of total input. It has the in as well as 2 bits of state. So it has, this combinational logic is a function which has 3 bits of input, and likewise it produces 3 bits of output. One is the out bit, which is what we are sending to the outside world, but then we also have 2 bits of next state. So it's really a combinational function which has 3 bits of input, and it produces 3 outputs, 2 bits of state and 1 bit of the real output. So this is nothing but that truth table. As you can see, it has 8 rows because it has 3 bits of input. Now looking at this, I can basically kind of talk about what the behavior would be. So let's say at some point in time, or maybe when the system powered up, so at the very beginning, current state is 0, 0. So somehow I arranged that my register, this D flip-flop, the two D flip-flops, which are also referred to as register. So my state has 0, 0. And let's say at that point in time, input is 0. And looking at this truth table, you can say in is 0, state is 0, 0, then the output is 0. So that's what we see out here. Now a clock tick comes. So what would happen is that we would now update the current state with what the next state is. So if you look at the same row, next state is 0, 0. So what happens after this clock tick is the new current state is still 0, 0, because that's what our truth table had said. What about now? Let's say in this particular after this clock tick, the external world happened to change the input to 1. So now in is 1. My current state is still 0, 0, and the output, again consulting this, in is 1 and current state is 0, 0. So we are in row number 5 from the top. So output is going to be 0, which is what we have out here, and next state is 0, 1. Now what will happen is another clock tick will come, and the state will get updated to 0, 1, because the next state is 0, 1 out here. So if you look at the animation again, now you see that state went from 0, 0 to 0, 1. Let's say input remained stable. The external world this time around did not change the input. So what the combination logic is seeing is 0, 1, and 1. So going back out here, that will correspond to row number 6, 1, 0, 1. And the output is therefore 0, so which is what we are seeing out here. So that's what we see, output 0. And next state is going to be 1, 1. Again, a clock tick comes. Now my state is going to move to 1, 1. So state moved to 1, 1. And let's say external world at that clock tick also changed the input to 0. So now, so remember, input is under this in pin is under the control of the external world. So it's changing it at sometimes whenever it decides. And I guess an assumption we are making thus far is it changes it just before a clock edge, okay, or at the clock edge. So we get to take a look at it. So now we are at state 1, 1 and input 0. So now we look at row number 4, which is 0, 1, 1. It says output is 0. So that's what we have out here. And next state is 0, 1. And again, at the next clock edge, you would see next state is 0, 1. And the whole process sort of continues. So I'm not going to walk through every row out here. But that's, I mean, these systems, one of the things about sequential systems is they run forever, right? I mean, you keep feeding input, they'll keep doing something. Okay, so now, so this kind of a diagram which describes what the combinational logic is doing is really at the heart of a sequential system, right? I mean, everything about how a sequential system is going to behave is captured in this kind of table which we have, which corresponds to kind of the truth table for the combinational part of my sequential circuit. Everything else is really sort of standard for all things, except for one stuff. One additional thing we need to know. So if you look at this right-hand side, there's one additional thing I had to assume to get this particular thing that we are getting over the clock tick. Can anyone think of what is it that I started out assuming? The initial state, right? What was the initial state? If I had started out with the initial state to be something different, the evolution is going to have been different. Okay, so that's a very important point, that with sequential circuits, the state matters because that is what is capturing kind of the history, right? I mean, it's almost like saying, let's say I clone someone and just change the memory in the brain of one person. Okay, so now I have two otherwise identical people with different memories, and we let them live. They are going to behave differently, right? Because they have different memories, different experiences. They're going to react differently. The same concept out here. So this initial state. So this is the initial state, and that is quite important in this. Okay, so now let's try to pop a level higher. So we can certainly kind of do this truth table and this kind of diagram over time and draw a waveform and all, but that's too messy, that's too low level. So what that brings to is a part of computer science which deals with something called finite state machines. So machines, by machine we mean a computing machine. So finite state computing machines are a specific type of computers. And it turns out that they correspond to our sequential circuits very nicely. In fact, you can say that sequential circuits of the type that we have are a way of realizing this class of finite state this class of computing, which is called finite state machine. They also go under the name of finite state automaton, state machines, and stuff like that. And you can think of it as an abstract computer, which can be in one of a finite number of states. Okay, so and by state we mean the entirety of the memory of that computer, right? Remember we talked about state is a way of capturing history. So a computer has memory, it can store data in registers in the CPU, in DRAMs, and on the disk, and the flash, and stuff like that. You sort of take all of it and you say that's what the computer knows about. What distinguishes one PC from another identical model PC is really the contents of its memory, its hard drive and stuff like that. Okay, so that is its state. So it's an abstract machine which can be in one of a finite number of states. Now, the finite number of states is true for any physical system. We don't know how to make physical systems which can have infinite state. I mean, even if you were to harness every subatomic particle in the universe, is still a finite number of them. Okay, so in reality, every computer is a finite state machine. In other courses, you will learn that why that's not always a good way of thinking about computing machines, and why we do like to think of computing machines which have infinite state, but then think of our real computers as an approximation of them. But here, we will continue to think of them as machines which have a finite amount of memory, and let's see what we can do with them. So at any given point in time, the computer would have some bit values in its memory, and that we would call as its current state. So as you can see already, there is an analogy that we are developing with sequential circuits, that flip-flops are the type of memory, and that's where the state is stored. The computer, this machine, changes from one state to another whenever it, if certain input patterns are observed. So for example, this is stolen from Wikipedia. If you look at this turnstile, which we encounter in many places, what happens is that it is locked, and then we kind of put a coin or swipe a card or do something. Then when it sees that, so in this particular case is a coin, then it goes to the unlocked state. It lets the moment someone goes through it, so this is the push event, that someone actually pushed the turnstile, then it goes back to the locked state. Okay, and while it is in locked state, you can try pushing it, nothing will happen, it will stay locked. And while it is in unlocked state, it can happily gobble more and more of your coins. This thing, this particular symbol with a dark dot and an arrow, basically says upon power up, you go to the locked state. So when the system starts out, it starts out in the locked state. So somewhere in the computer running this turnstile, there is one bit of memory which is basically knows whether this thing is locked or unlocked. In fact, that one bit of memory is probably driving the motors or the brakes or whatever mechanics that this guy has. So state is all the stored information at time t to which the system, the machine, the software on the machine, the circuit has access to. Okay, so that's the concept of state. And what we are dealing with now is computers which have finite amount of memory. Okay, and how do we deal with them? Now, there is a perfect analogy or with the sequential circuits we have seen thus far. So I have drawn the very same circuits we were seeing thus far, where I have combinational logic and I have these flip-flops, and they actually correspond to a particular type of state machine, finite state machine, which are called clock synchronous because they only operate at a clock edge. Okay, so this is the same thing redrawn The middle yellow box is my memory. This is the D flip-flops. That combinational logic, remember we had two parts to it, one which was deciding the next state and the other which was deciding the output. We have kind of split it out here. So I have this next state logic. It basically decides what should happen the next time. And I have this output logic which decides what is the output. And next state logic, if you see what it does is, it takes two things as input. It takes the input which is coming from the outside world, and it's also taking as input the feedback of the current state. And then based upon those two, it decides the next state. This output logic, what it does is, it takes the current state, and it may take the input coming from the outside world also, and use them to compute the output. And we had talked about two versions of it. One case where the output logic makes use of only the current state. That corresponds to a type of state machine which is called Moore state machine. Okay, so you see this little arrow. It's basically saying that for Moore type outputs, only the current state matters for Moore type state machines. For Mealy state machines, both the current state and the input come into play. And we had discussed last time around that with Mealy, what will happen is that in between clock edges, if the input changes, the output can be affected immediately. Whereas for Moore machines, since it depends only on the current state and the state changes only on clock edges, then the Moore outputs are only going to change when the clock edge comes. So that's how these two kind of end up differing. So this circuit which we had seen previously, if you compare with my abstract description of FSM, you can say that this is realizing an FSM except one which only operates on clock ticks. Okay, so it's as if our world moves from one clock tick to another clock tick and nothing in between kind of matters. So it's a special case of our finite state machine.
If your output logic takes a buffered version of the input for like a Mealy state machine, is that still considered Mealy or is it more?
By buffered, you mean?
Like instead of the top arrow going from input to output logic, if you put a buffer in there that's clock triggered,
then it will no longer be Mealy, it will be Moore. Okay, it's just that those additional registers are actually going to be part of your state. Okay, so what he's saying is the following. Let's imagine this blue line which is going up at the top. What if I were to put a register here also, a flip-flop? Then it will actually become Moore. Okay, because that flip-flop together with this flip-flop is your memory now. Okay. Question?
So is it only Mealy if the output changes, if the input changes in between clocks?
So let's wait. If it is Mealy, if output depends upon the input, I can draw a path from the input to the output without going through a flip-flop. Okay, that's the main point. Now, just because I can draw that path does not necessarily mean that my output will change, because I may have some stupid logic out here which always suppresses everything. Okay, but the idea is it is Mealy if I can draw a path from input to the output without going through any flip-flop. Okay, so what we have out here is a clock synchronous version of what this abstract notion of a finite state machine is. So Moore machines, this is the subset in Moore machines. What we have is, as you can see, the output logic is only dependent upon the state. And as a result, in this particular diagram, what you would see is if I look at the output U, it is changing only at the clock edges. In this diagram, they actually are showing some of the delays after the clock edge. So there's a little bit of a delay after clock. So, but the clock is out here. So this positive clock edge causes U to change out here. Then the second clock edge again causes U to change, and so on and so forth. So you would see every change in U is really only happening at a positive clock edge. That doesn't mean that at every clock edge U is changing. Okay, depending upon my logic, it may or may not change. So if the output from a state machine depends only on the current state, it is called Moore. Anyone knows who Moore was? Okay, you should go and check. These are some of these are all named after some famous people. Okay, Mealy state machines. So in case of Mealy state machines, my output logic also involves the input coming from the external world. So now this is what we have, and in this case, what you would see is that the output U can change in between clocks. So see out here how because of the change in X being our input, the output U is changing in between clock edges. Okay, so this is characteristic of a Mealy behavior. Now the advantage of Mealy is that output can incorporate effect of the input immediately without having to wait for the clock edge. The bad side is that if for whatever reason my input had a glitch or something like that, like transient signal change or something, which can happen, then my output will immediately see that also. So it tends to be problematic in design. In fact, one of the things that they often say is that good design practice means that your output of any module should always change only on a clock edge. That means it should come from a register or register followed by only a tiny bit of combinational logic. So Mealy machines are generally frowned upon for that reason. They can lead to kind of not very effective, lead to problems, but nevertheless, they're pretty powerful. There are special cases which really are still fall into the same category, but I wanted to show them sometimes. So sometimes you will see a machine like this, where output comes directly from the state. So there is no combinational logic in between. This is just a special case of Moore machine. Okay, it just so happens that the combinational logic is an identity function. Okay, so in this case, what is happening is that some of my state bits are also my output bits. Okay, that's really what's happening, but it's basically just a special case of Moore. This is another one where you will have a Mealy type machine, but at the output, we actually put a register out here. Okay, now looking at this, so you see this output logic, supposed output logic, and it depends upon input as well as current state. But the output of this output logic is not being sent to the outside world. We actually have another set of flip-flops out here, and then we are sending it. And it's called clocked Mealy output. That's the term which you will often see used. Okay, but it's really a Moore machine. Why is it a Moore machine? Right. So, if I were to imagine, if I were to redraw this machine, where what I were to do is incorporate this flip-flop also out here. Right. I mean, that's then this combinational logic, what I'm currently calling output logic, is really part of my next state logic. And then what's happening is that some of the flip-flops out here are going to be directly feeding to the output. So really, these registers out here, these flip-flops out here, really are part of my same state. It's just that I have drawn them differently. So clocked Mealy is nothing but Moore again. Okay, it's just a special case of special type of Moore. So anyway, ultimately everything is either Mealy or Moore. Moreover, Moore is a special case of Mealy. Stands to reason, right? I mean, if output logic does not use any inputs, then that's just a special case. So if I gave you a Moore machine and I say make a Mealy machine out of it, you already have that Mealy machine. It's just a special case. Going the other way around, going from Mealy to Moore is trickier. Now, these two machines are equivalent. There is nothing that one can do that the other cannot, or vice versa. So you take any sequential system, I can describe it in Mealy terms or I can describe it in Moore terms. No difference. The only difference would be that one guy may be delayed, shifted by a clock edge, but no other difference. But going from Mealy to Moore is a lot trickier to do. But again, there are systematic algorithms to kind of do it. So main point is, purely from a theory perspective, there is no computation that Mealy can do that Moore cannot, and there is no computation that Moore can do that Mealy cannot. Okay, they are equivalent. So that's so these are special cases. Now let's try to see that how this thing can be made use of to raise our the way we think about these systems. So at some point in time, my system is in some state. By that I mean that the state registers, the memory has some value in it. Okay, so I'm going to represent a particular value of the state by a ellipse like this, by a bubble like this, and I'm observing the inputs. I have some value for x being the input from the outside world, and a clock tick comes. Now looking at this logic, you can say, depending upon what x is and depending upon what the value of the state is, my next state will depend upon that. So I may have multiple choices of next state now. In fact, if I have s bits of state, then I can have 2 to the power s minus 1 actually to the power s possibilities for the next state. I can stay put, or I can move to one of any of the other patterns. So what may generally happen is I'm in a current state, and let's say x was a 1-bit number. Then depending upon whether x is 0 or 1, I'm going to move to some other next state. Okay, so in this particular case, let's say I had several choices, and I moved to this one, which is shown with the solid red. So after a clock tick, this next state becomes my new current state. And the whole process goes again and again, that every time, at every clock tick, I'm sitting at one of these nodes corresponding to the current value of my memory. And then I observe the input, clock tick comes, I move to one of the bubbles, or may choose to stay put. Okay, so every time the input comes, I may say, okay, I stay put here, or I move to one of the other bubbles. So I can think of this finite state machine as really moving from one ellipse to another ellipse at clock ticks, and it does so based upon what the value of the input was and where it currently was. So this abstraction is called a state diagram. So I can think of my state machine as in terms of a graph model, and this is our very same example that we had earlier, where this is a truth table for the combinational part, and previously we had drawn that timing diagram that trace what was happening on every clock tick. But now let's see what in terms of this graph model it will look like. So I said that the ellipses, the nodes in my graph, correspond to the different possibilities of current state I could be in. So since my state is 2 bits, I have at most 4 possible nodes. So I labeled them as 0, 0, 0, 1, 1, 1, and 1, 0. Now let's imagine I'm in state 0, 0, and a clock tick comes. What will happen? Well, if I'm in state 0, 0, then there are 2 rows which are relevant, the first row and the 5th row. If the input was 0, then this says stay put. The next state is still 0, 0. If on the other hand input was 1, it says move to 0, 1. So that's what's happening out here. If you see this first part corresponds to what the value of the input was. And this edge is as a result of this guy. It's basically saying that if I'm in state 0, 0 and input is 0, stay put. So loop back. This arrow where input says 1, this corresponds to this row. So according to this row, if I'm in 0, 0 and input is 1, then the next state is 0, 1. So see how we move to state 0, 1. Same thing happens, same logic we can apply to 0, 1. So if I'm in state 0, 1, there are 2 possibilities for the next clock tick. Input can be 0 or input can be 1. So I'm in state 0, 1, so the relevant rows are row number 2 and row number 7. If the input is 0, I go back to 0, 0. So that's what you see out here. If input is 0, I'm going back to 0, 0. So that is happening because of this guy. And if input is 1, then I go to state 1, 1, which is what we see out here. And same logic again and again. Now, I hope you would agree that if I were to give you this truth table, all the information is there, but the big picture is just not emerging. And I draw the same thing in this particular way, and immediately kind of pops out what is really happening. It's kind of like it moves from state to state, it can go back or kind of loop back. Okay, so the flow of the way the system is flowing from state to state is kind of more evident out on the right hand side. And you can reason about like what if I'm in this state, and if a particular input comes, what will happen? It's much more evident out here. The second number out here, so like when we say 1, 1, so that corresponds to the output. So if you look at again out here, I'm in state 0, 0. If the input is 0, then output is 0. And if the input is 1, output is still 0. So the second number on each edge is saying that if the input is such that this edge is going to be activated, then the right hand side also tells me that what is the output that I should be giving. So in this case is 1/0 or 0/0, so it's identical. But this last state is interesting. If you look at state 1, 0, what it is saying is if I'm in 1, 0, if input is 0, output is 0, and if input is 1, output is 1. And that's why you see If input is 1, then output is 1, and input is 0, output is 0. So that's the notation that we are using. And basically in this state, the logic is if input is 0, go back to 1, 1, and you at the next clock tick, and meanwhile your output should be 0. If input is 1, output 1, and at the next clock tick, go to state 0, 0. So exactly the same information which I have on the left hand side, but idea is that this is easier to reason about. Faced with a problem, you can this is almost like if you have written software and all. This is like the flow charts that we do, or kind of the flow of logic in our software. That's what's happening out here. Any questions on this? So very important point. There's no information which is on the left hand side which is not on the right hand side, and vice versa. Okay, they're representing exactly kind of the same thing. So that's the state transition, and input output. Now this particular version that I've shown is the one which book uses, and as you might imagine, when it comes to these formalisms and all, everyone uses something slightly different. I mean, the big picture remains the same, but there are some differences in syntactical details and all. So there are many tools out there, and they would have some minor differences. Different authors have slight changes and all. So what I want to do is I want to walk you through the formalism that specifically is used by the tool that we are going to be using. It's the best one I could find, which lets you draw these finite state machine diagrams, but it has slightly different syntax, almost the same, but slight differences, and I want to walk through it. And that's the tool called FISM that I mentioned. Okay, so what we have out here is a state machine drawn in FISM. And what this thing does, don't worry, okay, main thing to note out here is that I have states where there is a name. So the state has name called idle, read, delay, and done. So I can use these symbolic names, and later on I can decide what bit pattern I can make these things correspond to. See this state which has a double circle on it? That indicates the start state. Previously, we had talked about start state being indicated by that dot and an arrow going. This tool uses this double circle for the start state. So we have the state name, we have the start state. The outputs, at least in one very common variant, this is a very powerful tool, but the most common way is outputs are listed as a set of equations within each state. So for example, what this is saying is in the done state, the output RD is 0 and the output DS is 1. In the read state, output RD is 1, output DS is 0, and so on and so forth. So that's the output. And then finally there's a transition. So that's going from one node to another node. And you see how there is this little equation sitting next to the transition. It's saying go. This is another way of saying that take this transition if go is 1. Whereas in the previous case, we would have written just 1 or something like that, okay? So what you see is in the start state, if go is high, move to the read state. If go is low, remain in the idle state. And in this particular case, the system actually has two inputs. It has an input called go, and it actually also has an input called WS. So when I'm in the idle state, I only care about go. WS does not matter. So there are two choices. When I'm in the read state, there is this arrow going out here from read to DLY, and there is no annotation on it. It basically says always take it. Okay, so I come to the read state, and in the next clock tick, I will move to DLY. In DLY, again, we decide. So if WS is high, then I go back to read, and if WS is low, I go to done. And then finally, when I'm in done, then I always go to idle. So underlying state machine, again, doesn't matter. This is a particular example, but some of the notation comes across. Now, question, is this a Moore machine or a Mealy machine? Looking at this, can you say something? Moore. I heard Moore. Someone want to vote for Mealy? Okay, it's Moore. So why is it Moore? So exactly. So so the main point is all state equations have a constant on the right hand side. right? So if you look at each one of the four states, all the output equations. So in each state, the output equation is of the form output signal equal to some either 0 or 1, some constant value. So it's never dependent upon the input. So therefore, it is not Mealy. It is only more. It's only a function of the state. Now, there are variants to this basic formalism. So within the tool, so see in this particular case, there is an additional output called pre_RD, and that is set to go. So this is what makes it Mealy. It is basically saying in the state called idle, output pre-RD is happens to be equal to the go input, and therefore I am no longer dealing with a more machine. It is a Mealy machine. Okay, so this makes it Mealy. Another thing, it conveniences that they provide. So see out here in the idle state, previously, if I go back, I had two edges. One I had labeled as go and the other I had labeled as go bar. What this tool does is, if you don't label one of the edges, then it basically says that corresponds to the complement of whatever was out here. Okay, so that is implied. So it's called implied transition condition. In this case, the implication, since this condition was go out here, so the implication would be not go. Same thing out here. See how I have labeled WS out here, but not on this edge. Third one, if you look previously, everything here was equal. RD equals 0, DS equal 1, and so forth. But if you look at out here, some of these outputs have a less than equal to sign. And what this means is, it is telling the system that I want RD and DS to be actually bits in my state register, so that they come directly from the state, and as opposed to potentially through combination logic. So they correspond to, remember we had one of those state machines where the more output did not have a combinational logic, they were coming directly from the state registers. It was a special case. Same thing out here. So RD and DS, we want bits in our state register which directly correspond to RD and DS. Whereas for pre-RD, we cannot, in particular pre-RD is Mealy anyway, so I cannot have it come from a state register anyway. So these are additional conveniences / features that exist. Another one, further convenience. So we are lazy in drawing things, so conveniences come into play. So previously we had that, I left this loop back unlabeled and it figured out the label. Well, we say, hey, why even bother putting a label? A loop out here, just remove it. So what this is saying is, if I'm in idle and there's an edge going out and it has a go in it, I take this thing. By implication, we basically say, if this condition is not true, stay put. So that loop back is implied out here. Or likewise, no, there was no other loop back, so that was the only place where we had a loop back. So there is an implied loop back with an associated transition condition. So again, this is just to support kind of more compact writing. Final one, I can, if you look previously, we were putting a couple of slides back, we were putting pre-RD equal to go. Instead of writing it like this, you can actually write pre-RD equal to 1 on this transition. This transition is taken when go is true. So it's basically says if go is true, it's also the case that pre-RD is 1. Okay, so I can again, instead of putting the output out here, I can put it on the transitions, and which is what we were doing, which is what the book does. So these are all different ways of drawing things. If you are in the tool, you can use any version of these because the output would still be kind of the same. So again, Paul and Salma are going to kind of talk about some of these nuances, going through some examples. I have some more examples through the lecture, but what I would like to suggest is stick with a style. I personally like to make everything explicit because that avoids chances of making mistakes. So I would strongly suggest list all the output in every state. Do not list them on the transitions, and list every loop back and all, so that it's very explicit. Particularly because all of you are inexperienced, new to this stuff, so it's very good to make everything very explicit, because otherwise if you make mistakes, you yourself won't know that you are making a mistake. So leave these additional nuances, even though the tool lets you do it, out of the picture. The tool is actually kind of good in the sense that when it encounters these weird structures, it will warn you. It will put a warning in on the output saying, did you really intend it? I'm assuming this, but be careful. Alternate representation of the start state, like this or like this, the tool does not support it. Okay, so it only uses this double circle business. Questions. So this Prism tool, literally kind of just you draw nodes, connect them, and stuff like that, and then that's your starting point. And what we are hoping is to essentially give you something which then all the way takes you to a diagram which you can then enter into Logisim. Okay, I'm trying this tool for the first time, but it seems pretty good actually, and the only one I could find, at least the free one. So what we have seen thus far is, then we started out with circuits with memory. We said these circuits with memory could be thought in terms of how they perform over time, what happens at every clock tick, the truth table of their combinational logic. But then we said, all of that was too low level. We can think of them as these nodes in a graph, and we are jumping from node to node depending upon conditions. So faced with a problem, we would rather like to kind of draw this kind of a diagram and then systematically go from this to an implementation, as opposed to starting with combinational logic and low-level bits and all. Now, I'm going to take a very slight detour, and over the next sort of remaining next week or two in homeworks and all, you are going to encounter many different types of state machine problems. I'll say, design a state machine to do this or do that and all. They very broadly fall into three categories. They're like, you can think of them as classification of type of problems that you're going to face, and it's always good to think about like what is really happening. So there are three types that exist. One are what are called as acceptor machines, and I'm going to describe what they are. Another are called what are called classifier machines, and the third one is what are called as transducer machines. So let's see what they are. So acceptor machines, they are also called recognizer and sequence detectors, and what they seek to do is, they are getting input. Every clock tick, they look at the input, and they are on the watch out for a pattern in them. So like, for example, it could be a state machine which is observing characters coming in, and every clock tick there is a new character, and it's looking for a particular pattern in it. Maybe it is looking for the word UCLA in it, a substring called UCLA. Now, of course, there are two variants further in this thing. One is in which we say, inputs keep coming forever. And the other is, usually what we want to do is we want to say there's a special end of input indicator, and after that, don't bother. Okay, so it could be that I'm going to send you a word. At the end of the word, I'm going to put a special character, and after that, you should stop looking at the input. Input may still have some value, but it's a don't care. Main thing is that after the input has ended, in that kind of system, I want to look at your output, and if your output is high, then I would say my input passed a test. If the output is low, the input failed a test. So for example, going back to my example, I'm sending you characters, and you have to design a machine which is looking for the substring UCLA. The letters UCLA should occur in consecutive clock cycles, and at the end, I'm going to indicate the end of my input by putting a special character. Let's say it's a $sign. So I send you ABC, UCLA, XYZ, dollar, and then some junk characters after that. Then so you're going to look at the part up to the $sign and say, did the substring UCLA occur in it? If so, after the $sign, the output should be high, and otherwise the output should be low. Before the $sign, I don't care about the output. Okay, so that's an example. Or another example could be, I'm sending you bits, and I want to say that at any given point in time, if the input that you have seen thus far is going to be a number, if it's a prime number, output should be high. If it's not a prime number, input should be low. So output should be low. Or another example, again, sending you bits, and I basically say that if the number that you have seen thus far is a multiple of 3, output a high at that clock tick. If the number you have seen is not a multiple of 3, output a low. So every time I send you a bit, you have a new number, one more bit. You decide this. So these are all examples of systems where you are doing kind of a go, no go kind of a test. Okay, you are trying to decide whether some pattern is met or some rule is satisfied. So idea is then the states are of two types. There are accepting states and rejecting states. Accepting means my input passed a test. Rejecting means it did not pass a test. The test is what the problem is. So there's a binary output and a special. And if I don't want to look at the input after a certain point in time, then I'm going to give you a special marker. So for going by my example, so like for example, I said, let's say I give you A, B, C, U, C, L, A, X, Y, Z, dollar, and then again A, B, C. Then the dollar indicates end of input. So after that, you should have after dollar you should not change your decision, and meanwhile what is happening is starting from the first clock cycle you're looking for the pattern UCLA. Now this messy state machine that I have drawn out here actually does that, and I want to walk through that. Okay, so let's start with this thing. So we start with the start state. Okay, I have not seen any character. That's the start state. Output is going to be 0. Actually, output doesn't really matter. I've not seen the dollar sign, but I'm going to put output equal to 0. I really don't care. Now, as long if I get a dollar sign, that means my string has ended, and I have not seen UCLA, so I'm going to go to failed state. And once I reach the failed state, whatever I get, I'll stay put there. It doesn't really matter. So see, I have left this thing unlabeled, so I'm being lazy. I'm basically saying any character kind of stay there. Going back to my start state, if I see the letter U, so that I have labeled as n equal U, then I'm going to go to a state which I have called as found U. So what has happened is now I have said there's a potential start of a UCLA pattern. I have found the U. So that's this state. And if neither one of these conditions was true, I'm going to stay put in the start state. Now let's think about what happens in found U. If I get a C, well, I have now C, U, and C. So now I say I have found a C also. So I have met two characters of the substring. So that's one possibility. Another possibility is that I'm in the state found U, and I get another U. If that's the case, I should stay put here because it could be that I'm getting UCLA. Okay, so I stay put there. So that's why you see this loop back which says in equal U. And the final possibility, one more possibility is I got a dollar sign, end of string. If that's the case, I am seeing, I had not seen the complete UCLA, I've seen a U, and I get a dollar, so I am failed the test, I go to the failed test and put it out here. So that's a third possibility. And then the final possibility is, actually I just noticed that I have a typo out here, and this guy should say so it's basically saying if I didn't see a U and didn't see a dollar and didn't see a C, go back to the start state. Going to found C, same idea. If I get an L, I move to a state called found L. If I get a dollar, I move to a state called failed. If I get a U, if I get a U, then I go to the state called found U. And everything else, I go back to the start state, which is this edge. And then finally, if I get an A, yay, success, and I stay put there because I've seen the UCLA string and doesn't matter. I'm just going to stay put there. Eventually, the dollar will come, but I'm outputting 1. So you see, I have an out equal to 1 out here. So this is an example how sort of I took this specification saying you're getting characters, observe them until the dollar sign, and if you see the substring UCLA before the dollar sign, then output a 1 starting from the $sign, but you can do it sooner. I will only look at the output after the $sign. Otherwise, output should remain 0. So that's what this thing is doing. And really sort of coming from that description to out here, you have to come up with a strategy. And it's very common to kind of make mistakes and all out here. Like, for example, like one very common mistake I see is if you did not find the success and the $, you always go back to the start. That is not true, because if you're getting a U, you should go to found U as opposed to going to the start. Things like that. So you have to be very careful that you are accounting for every possibility. And if you think about it, this is no different than writing a piece of software. Okay, there's nothing really kind of specifically digital circuit about it. At this stage, you're really thinking of the algorithm, the strategy that you have. Question?
Why do you go back to start again? What's the condition?
Well, I mean, let's say, so I'm going back to start. So let's say I'm in found C. So I have 4 possibilities in found C. One is I got a U, in which case I go back to found U. I got the end of string, in which case I go to fail. I got an L, so I move further ahead. And if none of them are satisfied, I go back to start. Because it could be I was seeing the string, let's say, A, B, C, U, C, X. Okay, so A, B, C, I'll stay here. U, C, X, come back.
If you said it's like U, why should we, what's the harm in going back to start instead of staying at U?
Well, the problem would be, what's the harm in...
Well, you said we need to stay at the U instead of going back to start.
Because you have already seen a U. So let's imagine this is what happens. A, U, U, C, L, A. Okay? So, or let's say A, U, C, U, C, L, A. Okay, now in your example, what will happen is A, U, C, U, you will come back out here, and then you'll be stuck here because the next letter is C. Right? So consider this example. A, U, C, U, C, L, A, blah, 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 dollar, blah, blah, blah. Okay? So what will happen? A, you stay out here. U, you move to found U. C, you move to found C. Next letter is U. In my machine, it goes back out here. You are suggesting instead of found U, let's go back to start. So you go back to start. So now you have gobbled the U. Next letter is C, but you're going to be stuck here. Okay? So these states, as you can see, have a meaning behind them. The state found U means that potentially there is a UCLA and I have seen the first U of it. I've seen the U in it. The next, this says it's potentially UCLA and I have seen the C. This and that. Okay. There are certain words where things can get more complicated. Like, for example, let's say I want you to recognize, I don't know, Mamma Mia, M-A-M-A-M-I-A. Okay, well, you can, if you think about it, you'll have to do some additional stuff out here because there is a replicated ma. Okay, so when you fail, you have to decide where to go back. Okay, out there because there are repeating patterns within my substring. So again, this is really one about logic and all, and with practice you will think. But think about all these cases. Like, does your machine work for various sample inputs that you can see? Does it work for empty string? Does it work for when the pattern number is right at the beginning, right at the end, stuff like that? So just kind of mentally walk through this to see whether it's working. Question? More. Okay, so there's a general. So what these guys are doing is they have a binary output, right? Single bit output, success, failure. There's a class of machines called classifier. What happened?
Can you go over here why it wouldn't restart? So how come like you gobbled up your first U, but you have another U? So why didn't it?
No, hang on a sec. I gobbled this U.
Okay.
Then I gobble C. Now I'm here.
Okay.
Okay. Now question now is what happens when I see this U?
Okay.
You are proposing we go back to start.
Right.
Okay. If I go back to start,
Mm-hmm.
then when I see a C, I will stay put here.
Would it be possible to say when we go back to start, we don't gobble up anything?
No, you can't. Every time you were doing, the clock tick has passed, right?
Okay.
Yeah. So I'm now at the next clock tick, I'm seeing a C.
But then you have the U going backwards.
Yeah, I have the U going backward. I have every state, every time I fail, if I get a U, I go to found U. So the meaning for found U state is I have seen a U.
Oh.
Okay. Any other questions on this? Just make very sure that to sort of understand this example, what is happening. It's actually a simple example. You will face more and more complicated problems. Okay, so be very comfortable with it, and again, mentally follow what is happening out here. So these machines, these acceptor machines, which have a binary output, you can think of them as they're really defining a test, a language. They basically say they're taking a string and they're basically saying, is the string passing that test or not? And I can define any arbitrary test. So for example, the one I just did was I said S is a string and it has a substring UCLA in it, and if so, output is 1, otherwise output is 0. So accept a string if it has a substring UCLA. I could also say S is a string of decimal digits that form a prime number. Not primer. Okay. A prime number. That could be another machine. Or other examples I gave. I'm feeding you zeros and ones, and I'm saying if this thing is divisible by 3, or if this thing is a C program that calculates prime numbers, or whatever. It could be any test I can define, and I could say output 1 or 0 based upon it, right? Not everything can be done by a finite state machine of this nature, that I can define tests for which a finite state machine does not exist, but there's a large class of interesting problems where it does. So you can view this thing as a classification of string into 2 categories, those which pass the test, those that fail the test. A more general version of these problems is where we would ask you to classify a string into more than 2 categories. So I could say, for example, I'm giving you a bit vector, a string of zeros and ones, and you have a 2-bit output, and that 2-bit output should correspond to the remainder of this number with 4. So I'm giving you some arbitrary zeros and 1 string, and then I have 2 bits of output, and at the end of the string, after you get the dollar sign, for example, the 2 bits should correspond to whatever that number was modulo 4. Okay, then there are 4 possibilities, so I'm dividing the number into 4 groups: modulo 0, modulo 1, mod is equal to 0, mod equal to 1, 2, and 3. Okay, so this is a general version. I'm classifying into more than 2 categories. Same strategy, so I'm not going to spend more time over it. And then there are so-called transducers. Okay, so transducers are probably the more interesting from engineering perspective. So you can think of them as these are boxes which are always running. They're monitoring the input and are dumping an output, and that output is being used to control a machine or drive a motor or run a train or whatnot. So inputs they are getting from humans and sensors and whatnot, and output they're controlling stuff with it. So they're used very broadly in control applications. You find them in your cars and your aircrafts and like just everywhere around us. They could apply that output that we give can control speed of a motor, position of a shaft, or whatever, apply brakes, blink a LED and things like that. So unlike the previous example where we were kind of saying that, look at the string up to some end marker and then make a decision, here we are just operating forever. So that's an example out here. So give you a transducer example. And okay, so in this case, what we are doing is there is a 1-bit input. So you're getting stream of ones and zeros. And what I want you to do is, if the number you have received thus far, if the string you have received thus far has an even number of zeros, the output should be 1, otherwise the output should be 0. Okay, but you need to keep doing it. So the strings will never stop. There is no dollar sign. You're just getting zeros and ones forever. And what I want you to do is to look at the string you have received thus far and see whether the number of zeros is even or not. Now, firstly, one thing you have to decide is, can I even solve this problem? How much history do I need? Do I need all the bits I have received thus far? Not really. I need to keep track of whether the number of zeros I have seen is even or odd. So there are 2 states which are relevant. One basically says number of zeros that I have received is odd, and the number of zeros, number of zeros I have received is even, and number of zeros I have received is odd. And then I jump back and forth between them. So I start out in state S1, and then if I keep getting ones, I spin here. If I get a 0, I move to this state, keep getting 1, spin here. If I get a 0, go back. So let me show by an example. So let's say the string that you got was 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, and so on and so forth. So the first letter is 1. So when I start out, at the clock tick, I see a 1, and so output is going to remain 0 because I have not, hang on a sec, if output is 1, if it's an even number, so actually, since I have not seen a 0, so it's even number, so it's going to be 1. I see a 0, so now it's odd number, so output will become 0. So I will actually have moved to state S2. Then next 0, I'll move back to state S1. So I'll again get a 1. Then I'm getting ones, so I will stay put out here, 1, 1, 1, which is true because I have seen an even number of zeros. Next 0 that I get takes us to the odd, so again I move back to S2, so it becomes 0. It will remain 0. Next time I get a 0, again it is even, so I get a 1. Another 0, I go back to 0, 0, and so on and so forth. So that's the output. What's very important in this class of problem is, given the specification, you try to understand firstly what is the problem asking for before diving even to do this, and try to understand that what states do I truly need out here. Okay, so in this particular case, all I really cared about was is the number of zeros I have seen thus far even or odd, and that corresponds to my two states. And then I figure out a strategy of going back and forth between them. So state S1 represents even number of zeros thus far, and when I start out I have seen 0 zeros, so that's even. State S2 signifies it's an odd number, and that's what's happening out here. Questions on this example? Anyone? Not clear to anyone? Let's try another example. Output, so again I'm getting zeros and ones, and what I want to do is I say output is 1 if the number you have received thus far is divisible by 3. Okay, so let's take an example. So let's say I get 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, and so on and so forth. Let's say that's what I'm getting. I start out. So when I start out, I have not seen anything. You could say that I have seen 0, and therefore it is divisible by 3, and that is true. So I starting out output will be 1. When I see a 0, so the number I've seen thus far is 0. 0 is divisible by 3, so therefore I'll continue to have a 1. Then again I see a 0, so the number now is 0, 0. Is it divisible by 3? Yep, it is, so it is a 1. Then I get a 1, so I have now seen the number 0, 0, 1. It's not divisible by 3, so output should be 0. Then I get another 1, so the number I've seen now is 0, 0, 1, 1, which is 3, and therefore output should become 1. Then I get a 0, so it becomes 0, 0, 1, 1, 0. What should the output be? 1, because the number 6. Next one, I get a 1 now. So I get 0, 0, 1, 1, 0, 1. 13, not divisible by 3, becomes a 0. Okay, and so on and so forth. I'm not going to work through all of them. Okay, so the idea is at any point in time, I'm looking at all the strings, all the entire bit vector I have received thus far, and check whether it is divisible by 3. Now, of course, I've given the solution out here, so you can see it is finite state. You do not need all the bits. And the trick out here is to keep track of what is the remainder that the number I have seen thus far has with 3, and then come up with a rule. So what we have out here is S0, S1, and S2 correspond to saying, is the number that I have seen thus far modulo 3 0, or is it 1, or is it 2? There are just three possibilities, right? The number I have seen thus far, if it was divisible by 3, then I will be in S0. If it is divisible by, when dividing by 3, it has a remainder of 1, then I'm in S1, and otherwise in S2. Now, let's say I have a number which was divisible by 3, and I get a 0. So what is the new number? What's the relationship of the new number to the old number? Someone from the back. So I've received a bit vector. It's divisible by 3. I get a 0 at the end. What is the new number's relationship with the old number? On this side. So blue t-shirt. Yeah, you sir. Good. Multiply by 2. So if I have a number which was divisible by 3 and I multiply the number by 2, is the new number still divisible by 3? Yes, it is, right? So if I have an S0 and I get a 0, I should stay put there. Agreed? Okay. If I get a 1, the new number is the old number times 2 plus 1. Right? So if the old number was x and I get a 1, then the new number is 2x plus 1. As we just decided, 2x is divisible by 3. So 2x plus 1 would have a remainder of 1 with 3. So I should move to S1. So when I get a 1, I should move to S1. Agreed? Okay. Now let's imagine I was in state S1. And state S1 corresponds to that the remainder thus far was 1. Okay, so the number is of the form 3x plus 1. Okay, and I get a 0. That means I have a number which is multiplied by 2. So 3x plus 1 becomes 6x plus 2. There, as 6x is divisible by 3, so 2 is the remainder. So if I get a 0, I move to S2. If on the other hand I get a 1, so previously I had 3x plus 1, multiply by 2 plus 1, it becomes 6x plus 2 plus 1, which is 6x plus 3, which is divisible by 3. So I go back out here. And same analysis you can apply out here. So each one of these cases, we can think about getting a 0 means multiply by 2, getting a 1 means multiply by 2 and add 1. And then you can reason where you are going to jump in this. So this becomes my state machine for this.
Is there a way to prove that something is possible without actually doing it?
As in whether it is a finite state machine, doable with a finite state machine or not. If you are in CS, you will be doing courses on automata theory, and they do talk about some of these things, the problems which are solvable or not. So there are ways of, I guess, short answer, no. So just giving a problem specification, no. But there are certain so you can prove the other way around, which is there are tests that you can begin to show that something is not possible because it will require infinite number of states. Okay, I'll give you an example. To give you an example of a kind of problem which cannot be solved by a finite state machine. Okay. So you've all seen arithmetic expressions, right? Arithmetic expressions are, so let me, so problems that cannot be solved by FSM, by an FSM, I guess, yeah. Okay, so we have seen arithmetic expressions. So like they go like this, parenthesis a plus b times c plus d times e plus f plus g h plus blah, 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 blah. Okay, so parenthesis, operators. And let's say I ask you, make a machine which tells me, and so I'm going to give you an expression of arbitrary length, and I'm going to mark its end, and I basically want to say that when you get the end of the expression, tell me whether the parentheses were balanced. Okay, that's all I want. So I want to say, is it a well-formed arithmetic expression? Okay. Now, in this particular case, remember the string could be arbitrarily long. So I could have open parenthesis, a galore of open parentheses, and you have to keep track of it. You have to keep track of how many left parentheses you have seen. And there could be infinite many of them. So therefore, you cannot do it with an FSM. Okay, so that's an example. Now, having said that, I mean, is there like a program you can write to which you push in a problem and it tells you can it be done using FSM? No. And there are many other examples. And the thing is, there's a whole hierarchy of more and more powerful machines. And I think last time I had made the statement that the Turing machine is the most powerful machine in the sense that anything which can be computed, Turing machine can. And if it cannot, then it cannot be computed. Okay, so that's kind of the short answer. Yeah.
So then, is every modern computer a finite state machine because it does not have infinite memory?
It is, exactly. So every modern computer, and including if you have heard about things like quantum computers and stuff like that, they're all finite state in reality. Now, having said that, remember I just said this parenthesis checking problem cannot be done using a finite state machine, but we still do it.
So
right?
Put an upper bound on how long.
There is an implied upper bound. Okay, so we like to think about open parenthesis problem and all in terms of more powerful machines, but then we say some of them cannot be physically realized. So real machines are an approximation. So again, that will take us away from the topic of this particular course. If you're interested in these kind of things, take, I think, CS173 courses or whatever, they deal with finite automata theory, and they kind of go into these kind of properties. There are problems which cannot be solved, so they are beyond a Turing machine, basically. In fact, there are problems where even I give you the answer, you cannot tell me whether the answer is the right one, so you cannot even check for the answer. So there's a whole hierarchy of problems, but that's outside the scope of this course. But to answer his specific question, there is no easy way out here, and I will not ask you a question, can it be done using a finite state machine? Okay, maybe I should. Okay, I take it back. It sounds like an interesting question. Okay, can it be done using a finite state machine? But in any case, the idea is you cannot write a program which can take a description of a problem and declare that it can be done using FSM necessarily. Okay.
Is a program in FSM? Are all programs FSM?
In reality, okay. In abstraction, no. I can write a program which will work if you were to give me a computing machine with infinite memory. What will happen is, on a practical computer, it will give you an out-of-memory error. Okay, so a program that runs successfully is going to be finite state. Okay. So these examples hopefully conveyed to you how I can take these messy sounding problems and kind of translate them into a finite state machine. Now, you can also think of this FSM as kind of like a mathematical object. So one way of thinking about a mathematical object corresponding to FSM is that it has 6 parts to it. It's a sextuple or hextuple. I don't know what's the right term. It has a bunch of possibilities on input. So I have a bunch of input wires, k bits. So I have 2 to the power k possible input patterns that I can see. You can think of them as an alphabet. So in my example of UCLA, my input were letters. Letters are usually expressed using the so-called ASCII code, which what we are using in the design homework. They take 7 bits. So in that example, one possibility is that my letters they're represented as 7 bits. So my alphabet there was A through Z and 0 through 9 and so on and so forth. Likewise, I have an output alphabet. That is, I have some number of output wires and they correspond to output symbols, and that is the alphabet of my output. I have a bunch of states. So I have a set of states, and this is a finite set, which is what makes it finite state machine. I have a special state, which we call as the initial state, which is where we start out after power up. I have a function, delta. What it does is, for every state, given a particular I think I messed things up.
that sigma supposed to be up on the
Yeah, that's what happened, I think. Yeah, thank you. Okay. So, cut and paste problem. Okay. So, sigma is the input alphabet. So, what it's basically saying is for every state and for every possibility of the input pattern, I have a next state. So, that's my transitions. And that may include a loopback. And then finally, I have an output function, omega. And this omega can either be a function only of the state, in which case it's a Moore machine, or it could be a function of state and the inputs, in which case it's a Mealy machine. So I can think of it, finite state machine, as really this mathematical object and kind of deal with it, and which is how tools like FISM and all kind of do it. They keep track of what is sigma, what is gamma, what is S, and so forth. I mean, this collectively characterizes a state machine.
So is this kind of like a Markov chain, or?
So FSM and Markov chains are related. Markov chains additionally has a probability attached to it. Okay, so it basically says, seeing this with this probability, you jump to the state, with different probability, you jump to another state. Okay, so they are related, but here we are all deterministic. Okay. So, given a problem, I can write the state graph. Now, what does a design process look like? So, what I want to talk about is how do we take this FSM and translate that into a sequential circuit implementation. So the idea out here is that I'll give you some specification of the behavior of the system you have to design. You have to come up with a strategy. Only you can come up with it. Okay, I mean that's like the idea part of it. Then you are going to make a state diagram for it. You can either do it on paper pencil, or you can use a tool like FISM. There are other tools also, but I picked FISM because it works on any machine with Java, so Mac, PCs, and Linux machines. So that way I don't have to worry about what machine you have. So FISM does that. So you can draw the state diagram using FISM, but again, there are other possibilities also. Then recall here, I just gave states names, S0, S1, S2. But states ultimately are bits in a bunch of flip-flops. In this example, how many minimum bits I need in my state of state do I need? 2 at least, because I have 3 states, I need 2 bits. But I could have more. I could, for example, do one hot coding. I can have 3 bits of state. I could maybe have some other redundant coding where I can have 100 bits of state and whatever, pick patterns which are 100 bit long, indicate one of them to be S0, another to be S1, another to be S2. A lot of redundancy. So I could do any of these things. So there's a problem, which is what is the bit pattern corresponding to each state in my state diagram? That's called a state assignment problem. Again, you can do it manually, or you can do it, let tools like FISM do it. Okay. After this, there's a pure manual approach where, given the state assignment and given the FSM diagram, you come up with the state transition and output table, that glorified truth table for the combinational logic part we had seen, and we'll see how to do that. And then you actually design your next state and output logic using Karnaugh maps and all, and then design your netlist of gates, the schematic, let's say using Logisim. Or alternatively, there is an automatic approach where, so remember, we already talked about state assignment could be done automatically. Some of these tools then output the state machine in the form of a special programming language called hardware description language, HDL. There are 2 examples, 2 very popular examples of them, a language called Verilog and a language called VHDL. This Verilog language is scattered at the end of chapters in your book, so there are examples there. Again, this tool FISM can output this. So the FISM can take the tool, the diagram that you drew, and dump out a Verilog or a VHDL description of it. You can take this description and simulate it. So you have not yet designed the gates and the flip-flops. You only have the state machine, but you can simulate it, get the timing diagram, feed input, see whether it works correctly or not. And if there's a problem, you go back and fix your state machine, or in some cases, maybe your idea is wrong, so you have to even fix your idea. Okay, so once you are done with that, then you can use tools which are called synthesis tools, which take this Verilog and VHDL and then come up with a netlist of gates. Okay, they implement it. There are commercial strength tools called like companies like Synopsys and Cadence and all. And then there are some terrific open source tools which have emerged. So in particular, UC Berkeley has been a powerhouse in kind of designing these kind of tools in a long history of 20, 30 years. So using their tools and some nice wrapping around them and all, there is actually, I think the person in Australia was done it. So there is something called YOSYS. And what YOSYS does is it can take Verilog and it can synthesize the logic. Okay, it can map, it can take, it can do all that Karnaugh map and all, and actually a lot more, and essentially give you a bunch of gates and how they're wired up, gates and flip-flops and how they're wired up. And it can do so while taking all kind of things. You can tell it optimize for speed, optimize for number of gates, optimize for blah, blah, blah. Okay, so it kind of does that. It gives you that list. Now in commercial strength tools, that list straight away can then be used to make a chip and all, or program an FPGA. In our case, unfortunately, there's an inevitable manual step because none of these tools output in Logisim format. So they'll give you a list and then you'll have to wire it up manually in Logisim. Okay, there was a question there.
Can you convert from Verilog or translate from Verilog to HDL with not an tool, or are they a little bit different?
A subset of them you can. The thing is, the languages have different powers, so you cannot do it exactly. But most common designs, you can go back and forth, yeah. I mean, one way of doing it is you kind of read them into these tools into an internal format and then have them dump it out in that, so you can do it. So we're not going to teach you about Verilog and VHDL, but as you go through this tool flow that we are hoping to get it worked out a little bit, you'll see Verilog. And in fact, I'm going to show you some Verilog today. Okay, so just to the extent which is necessary to understand these state machines, we'll show you what the Verilog looks like. But by no means will teach you Verilog, okay, because you're not going to be writing your own Verilog. Okay. So this is the flow of the design that kind of happens. Manual approach. Previously in this course, that's what I have done. In fact, that's what they do in the other section of this course. As I like to experiment, and so experiment this time around is using FISM and all, I want to expose through this pathway because I think that's a lot more fun and it's a lot closer to how you will see in your work life if you decide to work in this area. Except that instead of using YOSYS, you'll use Synopsys or Cadence or one of these tools. Okay, but they're very similar. In fact, Synopsys tools grew out of the work at Berkeley, so just Berkeley work in 1990s. YOSYS is based upon the Berkeley work, which is more recent. Okay, so they have the same lineage. Okay, so let's go back to what things might look like. So this is the same state machine we had seen previously. You make it in FISM, and again, Paul and Salma are going to kind of walk you through some simple examples. Here I'm going to just show the examples to you. So the idea is that when you work in FISM, you kind of basically tell it what is the name of the state machine, what is the clock signal, is there a reset signal. The reset signal basically automatically takes the state machine to the initial state. So it basically says, is there a reset signal? If so, what is the name? And when the reset is there, which state do you want to go to? What are the inputs? I have clock, reset underscore n, go, and ws. What are the outputs? RD and DS. What are my states? Okay. This part you can ignore. What is basically saying is that RD and DS bits should be part of the state. I want them to come straight out of the state vector. And what is my default transition equations is basically saying if I don't put a label out here, it should mean you should always take that edge. Point is, I draw something like this. Okay, so thus far it is this drawing. It could be, I'll show you some other examples on kind of how to work with it. What this guy does is it outputs this Verilog, and in the process it does the state assignment for you. So let me walk you through what Verilog looks like. And again, you will not be writing this, so don't be spooked by it and all, because it's just a mass of program generated code. It says created by fism.pl. I did not write it. I just cut and paste. Okay, so it's basically saying that I'm designing a module called Cliff. This is a sample that we had. It has two outputs, DS and RD. It has 4 inputs, clock, go, reset n, and ws. It says, what are my states? So remember, I had 4 states, idle, delay, done, and read. Now, what this tool did is it did the state assignment. Okay, and remember, we had told it that I want out here. I had told it that I want RD and DS to come straight from the directly from the state bits. I want the hardware to be like that. I want my RD and DS to be directly coming from the states. So unfortunately, what that means is, if you look at out here, this pattern RD equal to 1 and DS equal to 0, okay, it actually is occurring in two different states. So if RD and DS are two of the state bits, then if they were the only two bits I had, then I could not distinguish between these two bit states. So I need a third bit. So in this example, therefore, what happens is that actually they end up using 3 bits of state. And this notation, like you see 3'B000, is basically saying I have a 3-bit binary number which is 000. DLY, its coding, the state corresponding to it is 010. For done, it's 001. For read, it is 110. It automatically did it for you based upon some criterion. You don't need to worry about it. It defines these things called state and next state. And then what it does is, see, it even puts some helpful warnings and all. But the main part out here is the following. This case statement, which I'm sure you have seen in your programming classes, is basically saying, depending upon what the current state is, if the current state is idle, if I see a go, next state is read, otherwise next state is idle. And then on the right hand side, it does the same thing for other states. It says if I'm in delay state and if I see WS, then next state is read, otherwise next state is done, blah, 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 blah. So it defines all that logic. And then at the end, what it does is it says at every clock edge, the current state gets its value from the next state. But what it also does is it says if I get a reset, then set the state to be idle. So it took care of all of that for me. I didn't have to kind of write this. Now, you could, if you are a power user and all, you'll probably write your own Verilog code. But again, in this course, and to be honest, I think for a lot of this stuff, I mean, that kind of visual look at the FSM is a lot more useful. So let the tool do the job. It will generate the state machine for you. And then from that state machine, you can get to a netlist of gates. That is done by Yosys. So what you do is to Yosys, you tell, I have these gates, I have this Verilog, figure out a way of implementing this Verilog using these gates. I have these gates and flip-flops. So it does that. Now, the nice thing about the reason we are picking Yosys and all is that there are good, easy ways of accessing it. One point I also want to say is I can give it a different library of gates, and then it will give me a different implementation. So this is a different implementation. If you go in here, it says NOT and NAND and stuff like that. Point is, again, details don't matter. It's a wiring diagram of gates, much like you draw in Logisim. Okay, this is dumping it out from the tool. This is another example. This is another state machine. Again, similar nature. You see how it talks about case the current state and then kind of do stuff in it and sort of set the next state to current state. There are many ways you can write this Verilog, which are kind of equivalent. Again, you can get a netlist out of it. All of this is done automatically for you. So our pathway is going to be, you're going to use FISM to design. So I'll give you a problem. You're going to first figure out your strategy, create the FSM in FISM, use FISM to dump Verilog, then use Yosys to get this netlist, and then manually, unfortunately, take that netlist and create the Logisim version of it. Okay, that path, maybe next year I'll have someone work it out. If any of you want to volunteer for a little bit of an internship and write a program to do that, talk to me. Okay, so the other thing is I said that Verilog you can simulate. I don't even have to actually go all the way to, I don't have to create the netlist, and I can just simulate at that level. So I can get a timing diagram and all out of that. So let me show you how this thing kind of works out a little bit. And if I am successful, then this should go well. Let's see. So let me switch to EduRoom. because I'll need a website access. Shucks.
You can run VPN on the wireless.
Yeah, that's what I'll do. No, it will not give me that. Okay. Obviously not cooperative. Let's try UCLA Wi-Fi.
Oh yeah, I do
Okay, it's not going to work out, so apologies. But let me show you how the FISM part at least works. And okay, so this tool called FISM. Okay, so as you see out here, this is the same example I was using in my slides. Okay, so I'm not going to redraw it, but the idea is that it has concepts of states, transitions, inputs, and outputs. So I can add new input and output by going to attributes, inputs, and if you see out here, I basically have all the 4 inputs stated. I can add, it also has support for multi-bit inputs, so like buses and all. I can add new inputs, I can set the colors and beautify them and all. I have outputs, same story. Out here, I have states. Now the way the states get created is actually you can either create them here, or you basically right click and you can do new state and all. Let's say I want to add a self loop out here. I can say add a loop back transition, and then it pops me up things and all. So essentially I can systematically go and kind of create my diagram. I can double click out here and then see out for each state. It lets me define what the value of the outputs are. So I can say RD has the value 0, DS has the value 1. It has a notion of default. So if I don't specify an output in a state, then it takes the default value that I have defined for that output. All of those things are there. What this guy then does is it creates a .fzm file, glyph.fzm, and actually if you open it up, it's just a XML format, it's an ASCII file. Okay, then there is the script called fism.pl, which is done using a language called Perl, which is standard on Macs. You may need to install it on Windows if you're on Windows, but we are hoping to provide you an approach where you don't have to do any one of them. You just give us the FISM file and then log on to a machine and then run it there. What this does is then produces the Verilog file, and which I had shown before. This is the Verilog file, and this is exactly what I had shown out there. Then you take this Verilog file, and then currently the easiest way is that there is this website called EDA Playground where Yosys is installed. So you upload Yosys and also Verilog Simulator. So you cut and paste your file there, and then you do simulation, and you can also get that netlist that I was talking about. But Paul and Salma are going to kind of walk you through that process. What I'm going to do next time we meet on Monday is to go through the traffic light example, which I had started previously, but I'm going to also sort of describe to you, or maybe we'll discuss, maybe we'll do that in the discussion section because I already have the files for it. So we'll walk you through this process, and then in the homeworks and design assignment, I would like you to try out the tools. So that's the plan.
Do you know how reliable those sites are? Like, if it comes to the times before the due dates, assignments, will sites go down?
You know, I am in discussion with them to get a private install out here, but they seem to be pretty reliable. And in any case, we will also create a Linux machine at our end where you can log in and run the tool. Okay? And the Windows version is ready to install. The problem is only for those who have Macs.